In this lesson, leveraging on what was previously presented in the case study, the methodologies adopted to generate simulations to predict the energy consumption in the operation of railway stations using the bottom-up stochastic modeling approach are presented. By constructing a separate module in RAMP for each kind of station, based on the parameters provided in the classification system adopted by Ferrovie dello Stato, we can categorize the railway facilities into 4 categories and related archetypes, as described in previous lessons. The 4 categories were modeled through RAMP functionalities, defining each station daily energy demand profile, and then aggregating them for the total number of stations present across the national territory as derived from publicly available data. Energy demand consumption spots have been determined based on the definition of different users and services. Larger stations with more extensive public areas are more likely to contain all the services for a higher number of visitors. The graph summarizes the distribution of services across the 4 station archetypes that have been defined in the proposed taxonomy. To properly initialize the RAMP model for energy demand simulation of railway stations, the number of each service present in each station archetype is randomly assigned within a feasible range, considering the varying sizes characteristic of each station class. Different users are defined for each different station archetypes. Each archetype can be characterized by the daily foot traffic, the size of each railway facility, including both travelers and non-travelers, and the average size of the station itself. Based on the examination of recent station projects, it is possible to quantify the area available for different services per station. We can distinguish between functions related to train services, and this is, for example, the traffic regulation, direct support services, ticket offices and security, and indirect support services, and this is, for example, the catering and commercial activities. The pie chart shows the distribution of the area occupied by each of the services. In the Italian railway system, services linked to each station archetype are defined using real data from the FS group. Platinum stations, the most complex, offer a wide range of services such as bars, newsstands, pharmacies, financial and postal services, restaurants, and so on. Bronze station, in contrast, may only have vending machines, lighting, and a ticket office. Gold and silver stations present a number of services between those of platinum and bronze station. By analyzing FS group data and dividing it by the total number of stations in each category, from the most to the least probable services for each station type were identified. This is reflected in the bar plot where the probability of finding different services in gold and silver station across the whole Italian territory is presented. As shown in the figure, for each route archetype simulation, we randomize the likelihood of finding combination of 3 or 4 different direct and indirect services for each station. For instance, for the gold station on Route 1, apart from elevators, vending machine, escalators and ticket offices, which are always present, it was assumed that there would also be a shopping center and a postal office, while for the station on Route 3, services as bars and pharmacies were considered. Given this framework, the energy demand of a single station is evaluated as the summation of the demand of all the services associated, multiplied by a frequency parameter. To this aim, RAMP software capabilities are being adapted to consider the multifaceted energy consumption of Italian stations. As mentioned earlier, a different user type has been defined for each station archetype to take into account the different number of services offered to the passengers. Within each user type, different users represent the services provided. Appliances are defined for each kind of service, considering what contributes to its energy consumption. In defining the energy consumption of railway stations, a comprehensive list of appliances is included in the ramp model. These appliances encompass a wide range of functionalities, including ticket machines, cash register, computers, and more. Each appliance is characterized by various parameters that influence its energy usage profile. For instance, while certain appliances such as lights maintain a nearly constant power value, others, such as computers or vending machines, follow different full load standby cycles. Additionally, seasonal variation impact the energy consumption of appliances like HVAC systems, refrigerators, and freezers, which are influenced by outdoor temperature changes. The ramp model takes these characteristics into account when defining each appliance through a set of predefined parameters. Now let's delve into some of these parameters. The quantity determines the number of appliances. The power rating provides the average power consumption of the appliance in watts. The number of daily time windows defines the number of distinct time windows within a day when the appliance is likely to be used. The total duration of operation specifies the total duration in minutes that the appliance operates throughout the day. The random variability in time fraction determines the percentage of the total usage time that is subject to random fluctuation. The functioning cycle defines the minimum duration in minutes that the appliance remains on after being switched on. This parameter accounts for the behavior of appliances with specific operational cycles. The simultaneous activation indicates whether all appliances of the same type are simultaneously activated or if they operate independently. The duty cycle count specifies whether the appliances operate continuously or experiences varying power cycles. The probability of occasional use provides the likelihood of appliance being utilized each day, expressed as a percentage. The power variability defines the range within which the appliance's power consumption can fluctuate. These parameters account for the variation in power usage due to different operating conditions or settings. And lastly, the user preference index considers the preference index for associating appliance usage with random user daily preference behavior. This parameter specifies which appliances can be used in each daily simulation based on the number of users addressing complex modeling situations in the sector. Special attention is given to parking and transit operation. Platinum and gold stations are typically destinations for trains rather than stops, serving as points where passengers disembark and board for the next trip. During this time, trains are usually connected to the station grid instead of using their own power to support onboard services and engine idling. This consumption is considered for both station categories, associating it with the average daily train trip schedule per station. By looking at some preliminary results that report the monthly energy consumption for a single station per archetype, we observe that, as expected, Platinum Station has the highest annual consumption and monthly average, resulting in around 7,200 and 600 MWh respectively, followed by Gold Station, Silver, and Bronze Station. The train services consumption has a significant effect on Platinum stations, accounting for more than 40% of the station's consumption. Considering that trains can be in transit service or parked during the day. On the contrary, in Gold Station, the train services consumption accounted for the 10% of the monthly consumption due to the lower frequency of trains, especially high-speed trains. The energy demand of all stations can be calculated by aggregating the energy consumption of different archetypes multiplied by the number of stations that belong to each category.